everyone. All right, so in this video, we're going to talk about electric potential energy. So now we have been talking about electric force. We've been talking about test charges, interacting with electric fields from other point charges. It makes sense that the natural next step that we're going to take is think about the type of energy that is stored within these little test charges, and that is electric potential energy. And that's given by this equation here. Our delta U sub E is equal to Q test times delta V. So the change in our electric potential energy is equal to Q test times delta V. And delta V, I'm going to write down that delta V is something we call an electric potential difference. Oftentimes people will just say electric potential, but I'll make it really clear that this is an electric potential difference. So we have some test charge, and it's going to be interacting with some electric potential, and it will in turn be stored as electric potential energy. So this is really similar to what we've been working with already, right? We've seen that the electric force is equal to Q test times the electric field. So if we have some test charged particle here, and it's sitting in some electric field, it will experience this electric force. In a similar way, if we have this test charge here, it interacts with some potential that we're going to talk about in the next video, and it will store this potential energy there. This is very similar to gravitational potential energy. So I'm going to just do a little side-by-side comparison here. I'm going to rewrite my electric potential energy is equal to Q test divided times delta V. And then when we were thinking about gravitational potential energy, we still have a change in our potential energy, U sub G. This is equal to the mass of the object times G delta Y, right? MGH, maybe you've seen it written as previously. These forms look very similar now, right? In this case, we've got a test charge that has some change, is feeling some change of potential, and it will store it as electric potential energy. In this case, we have an object that has mass m. It changes its height above some, like Earth. It changes its height on Earth, and it will store that as as gravitational potential energy. So they're very similar. They work very similarly. So in a sort of similar way, right? We have our delta V. This is our electric potential difference. And we can kind of say a similar thing with G delta Y here. This is like our gravitational potential difference. Gravitational potential difference. Another good thing to investigate here are the units. We know that we've got energy on this side, so we've got to have joules. We've got coulombs here. This is a coulomb. That means that this delta V has got to be joules per coulomb. And we can go back over here and see a similar sort of thing happen where we've got joules on the left-hand side. This is equal to masses in kilograms multiplied by, that must be that this part here, our gravitational potential difference, has got to be joules per kilogram. Just another similarity between the two. So if you're comfortable with gravitational potential energy, then we're going to treat electric potential energy in a very similar way. In the next video, we're going to talk more specifically about what this electric potential really means.